Okay, welcome to week 3. And the key concept we're going to do is ask, how does R get your design matrix? How is it doing that? So, we've got week 3. So let's recap our model. We'll just be coming back to this again and again. So y equals x beta plus epsilon. And that x we call the design matrix, and it basically tells us for each observation what are the predictors. That's it. How does R do that? Well, if you think about it, if we go lm and we go y tilde x, and that little squiggle is called a tilde. If we go y tilde x, that is giving us information. In fact, that thing, the y tilde x, is called the model formula. And in R, it's represented as a formula class. And the basic rule is anything to the left of the tilde is response variables. And notice I said response variables because you could have multiple ones. We've always only had a single one. While everything to the right is used to get your design matrix. It's all your predictors. Now, I'll come to the end of this. I'm going to go work through lots and lots of examples in R. If you want to run the examples yourself, you will find on my uni, there's a thing called Stats Modeling, Case Study 3, Model Formula.rmd. So just when you're reading these notes, you know what to come back to. So basically, we can do multiple regression models by, instead of having a single x to the right of that tilde, we can have lots and lots of predictors separated by plus. And we'll come back to this in the next lecture. We can also do functions. We can build functions directly in. So I could actually, if I wanted to take, for example, the log of my response variable, let's say my response variable is FVC, I can put log, brackets around it, FVC. I can also take logs of predictors. So I go log, brackets FVC, tilde, log height. So now my predictor of the log of FVC would be the log of height and weight. Now, obviously, sometimes you might want to, for example, take the square of a term or the cube. The problem is plus, minus, times, divide, and what we call the caret, that little hat symbol, they have special meanings to R in the formulae. So if you try to do x hat squared, R would think you're doing something different. And we will talk about what those various things mean in the next lecture. So instead what you have to do is you have to say, nah, don't do that. I actually want to use it as a plus or a minus or times or a divide or a hat. And so what you do is you want to inhibit R doing its clever things. So we have a function called the inhibit function. So you go I, bracket, and you put the stuff inside that you don't want it to do. So if you want polynomials, so you want squared, cubed, if you want to divide things, times things, plus or minus, you put them in an I and brackets. So you basically say, leave it as is, do what it says. But the main thing I want to talk about in this particular topic video is how we deal with categorical predictor variables. Because if you think about it, most of our predictor variables are numbers. Well, a categorical is going to be, labels. It's going to be words. And so we need to say, how do we convert words into something that's numbers? And there's more than one way of doing this. First of all, just to recap, a categorical predictor variable in R is called a factor. So you often hear me talking about factors and categorical interchangeably. So we're actually going to, the final topic video of this week, we're going to actually look at a case study looking at poison. But let's think about what this is done. And I'm very sorry if this is just really sick. This was done a long time ago. But basically, they did an experiment where they took animals. Let's assume that evil, horrible animals, we'll go cockroaches, that makes you feel better, were exposed to one of 3 poisons. So the first categorical variable is poison, and it has 3 levels. We also had 4 different treatments. So our second categorical variable is treatment, and that has 4 levels. And we measured the survival time recorded for each animal. That's unfortunately how long it lasted until it passed away. And for each possible combination, we did 4 animals. So we've got 3 different poisons, 4 different treatments. So we have 12, altogether 12 different combinations. And then we did that times 4. So this is what we call a 3 times 4 factorial experiment with replication 4. Factorial just means we looked at every single combination. And for every combination, we had 4 animals were exposed to that. As I said, we'll come back to this case study. But one of the things I want to talk about in this topic video is the theory of how we could represent it. So this was done in 1964. Well, the data was analysed in 1964 by someone called Box and Cox. And they previously determined that if we set our response variable to be 1 over the log of the survival time, then we could use this model. So we're going to say, for the ith poison, the jth treatment, and the k animal in that group, we have an overall survival time plus some extra amounts for the type of poison, plus some extra amounts for the type of treatment, plus we've got a noise term. So we've got E, I, J, K, and we'll assume this is normally distributed minus 0, variance of sigma squared. So the I tells you about the poison, the J is about the treatment, and the K is labeling the animal in that group. The problem is that's non-identifiable. Basically, if you try to fit this model as it is at the moment, and you said, what I'll do is, for all the alphas, I will have 0 if you're, basically, you'll have a column in your design matrix, which would be 0 if you're not that poison, and a 1 if you are, and you did the same, you'd have a column for each of the treatments, and there would be a 0 if you're not that treatment and what you are. So we've created these columns that are just 0s or 1s, and 1 says, I had that treatment, or I had that poison. If you did that and you got your design matrix, it wouldn't work. You've overfitted this. It's non-identifiable. Basically, you have too many parameters for what you basically, the data you're observing. And what this means is if you look at your matrix and you try to solve it, you don't have full rank. It's not got unique solutions. There will be infinite number of solutions. So what that means is when I look at my model matrix X, the columns would not be linear independent. So what we have to do is we somehow have to get rid of a column or a couple of columns. And so we have to impose certain constraints. And there's two classic ways of doing that. There's actually more ways of doing this, but these are the two classics you see most of the time. The first approach is you can say, right, I will make it that with my coefficients, I will make the sum of all the alphas equal to 0 and the sum of all the betas equal to 0. And this is called the zero-sum constraint. So basically, by doing that, you lock one of your alphas in and you lock one of your betas in, and that reduces your design matrix so it works. The other thing we can do, and it's the one that's most commonly used in R, is what we can do is we can choose a reference level. So we look at it and we go, we will choose the first one alphabetically for each poison and the first one alphabetically for each treatment, and we will set them to 0. Because they're 0, you can get rid of that column. Again, you solve the problem. Now the question is, this changes how we interpret the coefficients. So in the zero-sum constraints, the alphas we get tell us how much treatment I will lie above or below the average of all treatments. While if we do the treatment contrast, which is the reference level one, the alpha I tells us how far the mean of treatment I is above or below the mean of the reference level. And if you've done any ANOVA in R, or you've done any ANCOVA in R, which you should have done in stats model inference, you would have seen this already. You often get these coefficients and you sort of go, ah, this is how much above the reference level I am. What about interactions? Well, if we wanted an interaction, let's say in this case for the poison, we have some replicates, so we can add an extra interaction, a gamma I J. Again, we're going to need extra constraints. In fact, we now need 2 extra constraints, so we'll set that the gamma I1 and the gamma 1J are both equal to 0. What do we mean by interactions? You'll see this when we start looking at examples. All you're going to do to get the interaction term is find the 2 relevant, in this case, poison and treatment columns and multiply them. So your interaction is just going to be 0, 1s based on doing that multiplication, and we'll see that. So this is just me saying, reminding you that the way we do all this is it's all done under the hood. You don't have to do it, you just use the factor command. The plus I'm going to get next time. Let's now go to R and have a good look at some of this stuff. So here's my model formula. So I'm doing this all in R Markdown. So first thing is I'm going to create us some data. So I've got a tibble, which is, remember, just a fancy data frame. We're going to have a Y, which I've just put some numbers in. x1 is going to be the numbers 1 to 5, and x2 is going to be basically, that command sequence says go from 3 to 11 in steps of 2. So it's going to go 3, 5, 7. Don't believe me, we run it, and oh, that didn't work. Let's try again. Oh, could not find function. Forgot to load it. Sorry, let's load it. Nice. Now let's run it. Much better. So there we go. Here's our little tiny data frame. It's got 5 rows. It's got 3 columns. Here's our response variable. We've got x1, which is our first predictor, and x2, our second predictor. The way we can look at what R is doing is, rather than running a linear model every time, we can just use this model matrix command, which you saw in the, I think in the first prac. And what this is saying is, make me the design matrix as if I had a single predictor x1 using that data frame. So if we run that, all it does automatically is it always gives us an intercepts column, which is a series of 1s. And in this case, x1 was just a nice little numerical, so it went 1, 2, 3, 4, 5. That's it. That's your design matrix. That's your x that it's going to use in your model. If I use the plus, so I have 2 in there now. Again, it just adds now 2 columns. The plus is just adding extra columns in this case. So you've got your x1, 1, 2, 3, 4, 5, and your x2, 3, and this is your design matrix. And it's got some extra stuff here because it's it's letting it know internally what's going on. We can do a function here because this won't necessarily. I wonder if it would work. I'm just going to try something. Let me just do model matrix. Yeah, that still works. Cool. But anyway, I did it with a linear model. It's a bit confusing. Don't know why I did that now. Anyway, if I did the model matrix, you can see it does have some problems because we had some zeros, and it's been clever. Where it tried to take the log of something that was negative or 0, it's just removed it. So you can see that, just to remind you where we were, we had our data frame. This one, and this one, you can see in red, are negative, so it can't do them, so it made a design matrix. Important to know. It warned us. It said, oh, by the way, something's going on there. But suddenly your design matrix is only got 2 columns in it. So 2 rows, 1 and 3. With this one, we will now do the log of y tilde log of x. So there's now my model. And if I did the model matrix of that bit, you can see here there's no problem. All these were basically non-negative. So here's your intercept. It's taking the log of the x1, and there's your x2. What about the indicator one? So let's say I want to do x1 squared. If I did that, no problem. It is exactly what I expect to do. Here's x1, and this column is taking every element and squared it. So 1 squared becomes 1, 2 squared becomes 4, all the way to 5 squared becomes 25. What happens if we did something like, and I'll go in more detail about what the square is doing, if I did this, so I forgot the I, it seems to have also forgotten and what it's doing, and we'll talk about this later, is the squared is putting in an interaction term of x1 and x1, and x1 interacting with x1 is x1, so it didn't bother adding it. It's actually quite clever. It will look at your columns and it will basically remove stuff it doesn't need. It tries to avoid you having linear independent. To show an example here, I'm going to do the standard plus. And here it basically has 2 columns exactly because we've got 2 predictors, x1 and x2. But if I put an I around that, what does it do? What it does is it takes them and it adds them before doing it. So when 1 plus 3 is 4, 2 plus 5 is 7, 3 plus 7 is 10, etc. So this now, it went and added these 2 things together rather than saying, you have 2 predictors. So now we're going to have a look at factors. So I'm going to set myself up a new data frame like this. So we've got in A, I've got level 1, 2, 3. And in B, I've got 1s, 2s, and 3s. And I put levels so you can tell the difference between A and B. So let's do a model matrix of A. No problem, it's done of 0 reference. So it said, what's the first one alphabetically? Level 1. We'll set that to our reference level. And then basically now it's got 2 extra columns. So if you have K levels, you'll end up with k minus 1 columns. So this basically is a 0 if you're level, any level but 2, and a 1 if you're level 2. So you see this one's level 2, so there's a 1. This one's level 3, so now with this column, you're 0 if you're anything but level 3, and you're 1 if you're level 3. And the question is, well, how do you get level 1? Basically, to be level 1, you've got to be not level 2 and not level 3. So this gives you your level 1 levels. And it tells you you've got contrast and everything. So let's now do that with B. And it's gone wrong because let's go back and look at this data. If you look at the top of the table, it says A is a character, and characters it knows, well, you forgot to convert that to factor, I'll do it for you. B, it's an integer. It's like, fine, it's an integer. I don't need to change anything. So what we need to do is I'm going to mutate it. I'm going to actually take my data frame, then I'm going to mutate it such that B equals factor B, and I'm going to save that as my data frame. And now I'm going to do my model matrix. Now you're getting what you expected. So these first 3 are all level 1. So they're all zeros in both. Then the next 3 are level B, level 2. So they have 1s. And the last 3 are level 3. So they have 1s. But notice I had to tell R, just because you know it's a categorical doesn't mean R knows it's a categorical. Now, let's grab some more data, like that. And as you know, I'll do this next time. We'll come back to this. We'll do this fancy one with pluses and minuses and all that in the next topic video. So that's it. That's your factors as done. And next time we'll come back and we'll start looking at plus, hat, minus, etc. and see what that means in terms of design matrices. Okay, see you next time.